So today I'm going to do a small seminar on the topic measuring distances in astrophysics. The traditional way of measuring distances in astrophysics is known as distance ladder. Any given method of measuring how far an object is works only for a given range of distances. So what we do is we use one method for nearby and use that to calibrate the next method, which gets you a bit further, and use that to calibrate the next, and so on. It can be considered as a rungs in the ladder. And the first and the simplest step is called the parallax, a method purely based on geometry. It is essentially just taking the motion of the earth around the sun. As the earth moves around the sun, it causes our viewing angle to shift slightly, making nearby stars move relative to the far distant background stars. The parallax angle is defined as the difference in apparent position if the earth is moved by one astronomical unit. If parallax angle is equal to 1 arcsecond, it lies at a distance of 1 parsecond. 1 parsec is equal to 3.086 into 10 raised to 16 meter. But here the problem is that 1 arcsecond is a very small unit, and also there are no stars within 1 parsecond. The nearest star is about 1.3 parsecs away. Even the best background based telescopes can only measure parallaxes to a handful of nearby stars. Using the parallax method, the Hipparchus satellites were able to get us to the nearest cluster of stars, the Hyades cluster. So in order to go beyond the Hyades cluster, we go on to the second step, that is the main sequence fitting. We know that most stars are burning hydrogen to form helium. The rate at which this happens depends upon their mass, which tells us their temperature. When we plot their luminosity against their colors, we find that they lie in a line called main sequence. More massive stars are luminous and hot and therefore appear blue, while less massive stars are faint and appear red. So in the graph shown here, we can see lower mass stars in the bottom right, and as we go up, the stars are heavier and follows the main sequence. We then go out to the nearest easily observable galaxy, the Large Magellanic Cloud. We measure the fluxes and colors of a lot of stars in the Large Magellanic Clouds and identify the main sequence. We then look at how much fainter stars of a given color are compared to similar stars in Hyades. We know how far Hyades is using the first step of distance ladder, that is the parallax method. So consider two stars of same luminosity L. Their observed fluxes are given by inverse square law. F is equal to L by 4 pi d square. If we have two stars D1 and D2 of same luminosity, then the ratio of fluxes gives us D2 is equal to D1 into root of F1 by F2. Using this, we can measure distances to Large Magellanic Cloud. Unfortunately, we cannot get distances to any more distant galaxies. So in order to go beyond Large Magellanic Clouds, we use the next step in the distance ladder, known as Cepheids. To go beyond Large Magellanic Clouds, we need something brighter than the main sequence stars, and also we need it to be common enough so that we can find it in the Large Magellanic Clouds. These types are called Cepheids. They are giant stars which we can see in a much greater distances. These pulsating stars are easy to spot. The luminosity of Cepheid variable correlates with their pulsation period. This calibration measured in Large Magellanic Clouds where there is a lots of Cepheid variables. So if we see something with a given pulse and luminosity, and then we look at pulsing stars in more distant galaxies and use the ratio of fluxes to calculate the distance. But still, that's only far enough to get us to a handful of galaxies. In order to get more, we move to the next rung, which is known as Tully-Fisher. Using galaxies in clusters, it has been found that for certain types of spiral galaxy, their luminosity correlates with their rotation speed, in the sense that brighter galaxies spin faster. This tells us that the amount of dark matter in a galaxy, which determines the rotation speed, correlates with the number of stars, which determines the luminosity. We can use the Doppler effect to measure the rotation speed and hence the luminosity. The flux then gives us the distance via the inverse square law. Unfortunately, there are very few spiral galaxies close enough to measure their distances using Cepheid variables. So the Tully-Fisher relation is not well calibrated. It is also not very accurate. There is an 18% scatter in distances measured using it. So in order to go beyond this, we use the next step called type 1a supernovae. The Type 1a supernovae is one of the largest explosions in our universe. It results when a white dwarf, which is a ball of electrons, reach a point where the whole ball ignites and convert the carbon and oxygen into nickel, cobalt, and iron. This produces a huge ball of expandable junk, which is incredibly bright. It has been seen that all these have the same luminosity. It turns out that their exact peak luminosity correlates with how long they stay bright, and using this relationship, they can be used to produce quite accurate distances. And they are so bright that they can be seen out to enormous distances. Unfortunately, few have occurred close enough that we have some other way to measure the distances. So while we know that they all have the same peak luminosity, we have trouble knowing what this peak luminosity is. So we have discussed about the 5 rungs in our distance ladder, and each of them has its own problems. The problems all multiply together as we move up the ladder. So the end result is almost uncertain. So in order to tackle this problem, new techniques have been developed. One of the main techniques is the Hubble Space Telescope. The Hubble Space Telescope was deliberately designed to observe Cepheid variables in much more distant galaxies than is possible from ground-based telescopes. It can use Cepheids to measure distances to galaxies out as far as 13 megaparsecs. This means you can measure the distances to a few galaxies that have hosted Type 1a supernovae, and also you can better calibrate other distances indicators such as Tully Fisher. In addition, the fine guidance sensor on Hubble Space Telescope turns out to be a really precise way to measure parallaxes, and has measured parallax distances to a handful of Cepheid variables in our own galaxy. These distances allow us to bypass the Large Magellanic Cloud in building up our distance ladder, which is important because the Large Magellanic Cloud has a much lower abundance of heavy metals than most big galaxies, which may bias things. In addition, infrared cameras on Hubble Space Telescope allow measurements of Cepheid at infrared wavelength where dust is less important. Another method is eclipsing binary distances. The distance to the Large Magellanic Cloud remains a big problem, but several new methods are improving our knowledge of this key distance. One is the use of eclipsing binaries. Microlensing survey telescopes find widely separated binaries with edge-on orbits so that the stars pass in front of each other, causing dips in the brightness. By combining spectral Doppler effect measurements, the brightness measurement, it is possible to measure how fast the binaries are moving, and hence how long it takes them to cross their radii. Optical interferometers on Earth allows us to measure the surface brightness of nearby stars with the same colors as these eclipsing binaries. Surface brightness is the brightness per unit observed solid angle and is independent of distance. If you assume that the stars in eclipsing binaries have the same surface brightness as those with the same colors in our galaxy, you can thus work with their luminosity and hence distance. This currently gives distances accurate to about 3%. Another method is known as the mega-maser distances. Some active galactic nuclei, like giant black holes in the middles of galaxies, are strong sources of maser emission. This maser emission comes from blobs of gas orbiting around the black hole in some sort of disk. Because the maser emission is so strong, it can be observed by radio telescopes using the technique of very long baseline interferometry, in which telescopes all over the world combine their data to get extremely high resolution. This allows us to see the positions, transverse velocities, and accelerations of individual blobs. By combining all this information, it is possible to derive the distance to the mega masers using only geometry and the laws of gravitation. To do this, we need to observe at least one gas blob off to the side of the disk and measure how far it appears to be from the black hole, and from the Doppler effect, its velocity v. We also need to observe some blobs in front of the black hole and measure their apparent transverse velocity phi dot, their acceleration a. Combining these, we get a distance given by the equation as shown.